Welcome everyone. This is Data Driven Dude back with another video on an important concept in machine learning. Today we are discussing bias variance trade-off. Actually, it's bias variance error trade-off, since the actual trade-off is on the error metric. Let's start by defining the two important terms here, bias and variance. So starting with bias, it's a measure of model accuracy to predict true relationship between input and outcome variables. So models with high bias, they tend to oversimplify the underlying distribution, resulting in high training and test error. Models that are able to fit well with training data set, they have low bias. And these models also tend to be more flexible. Now variance is a measure of model accuracy variability on unseen test data. So models with high variance, they haven't captured the true relationship between input and output variable. Instead, they have overfit the training data and are more of a lookup table for training data. Models with low variance, they have actually learned the true relationship between input and output variables, and they will have low error on unseen data. Now let's look at some visual examples to understand various permutations of high/low bias and also high and low variance. The purpose here is to have a visual picture in mind to differentiate between various cases of bias and variance. So here's the first plot. As you can see, the predictions are clustered together, which can be interpreted as low variability, but it's further away from true center and hence has high bias. So this first case is of a high bias and low variance. Now in this case, the predictions are neither clustered together and nor are they centered around the true center. This is actually the worst case possible. This is where it's high bias and high variance. In this picture, the prediction seems to be centered around the true center, so that means they have low bias, but they are not clustered together, they are further apart, so that means they have high variance. And coming to the last picture, this is actually the perfect case possible. That's because the predictions are clustered together nicely around the true center. This is what we are aiming for whenever we train any machine learning model. Next, we'll see some bias variance example on regression problems. So here's a plot of some data points. Let's say we want to start really simple. Let's pick a linear model. This is what the best fit line would look like. By looking at the fit line for the data points, it seems to be oversimplifying the relationship between input and output variables, which means it has high bias. That's the reason it's not fitting the training data well. And the reason for high variance is that it doesn't generalize well over the data points, and hence will have poor performance on unseen test data. Now to improve on previous result, let's go with a slightly more complex model and train the model for a bit longer. This is what the fit line would look like in that case. It seems to be a quadratic model that does seem apparent by looking at the data points. And the line does seem to fit the data well in general. It captures the trend nicely. On surface, this seems to be the best fit to the data points and hence has low bias. And also, since the line does fit the data well in general, it will also fit the unseen data nicely and hence has low variance. So this is the low bias and low variance case. Now let's get a little bit crazy over here with the model and keep on training the model until the training error either goes to 0 or goes as close as possible. This is what that fit line would look like. As can be seen, it fits the given data really well, almost to the point where it will spit out the exact output value given the input data point. So it has low bias. But as a result, for training the data for too long, it has become a lookup table for training data and will not fit well on unseen data. That's why it has high variance. So as you can see, we started with both bias and variance as high and then improved in both bias and variance. But if we kept on training for longer, the variance value again starts to get worse. There's a sweet spot somewhere in between that we are aiming for. So I'll just say keep that in mind while we continue to explore this topic further, because this is what that sweet spot that we're looking for. Now let's repeat the same exercise for a classification problem. We have data from two classes represented by orange and blue colors. Let's start with a simple classification model. It's not a bad one to begin with, but a lot of blue data points and few orange data points are misclassified. Now this has high bias and high variance, since it performed bad on training data and also on test data. Let's continue training this model for a bit more. This is the classification boundary that the model came up with. This one looks a lot better than the previous one. There are few misclassification examples, but looks like this is probably the best classification boundary for these data points to avoid training on the noise. So this one has low bias and low variance. Now if we choose a more complex model and let the model to continue training until the training error is low, this is what we'll get as the decision boundary. On surface, the training area error is 0 since the boundary correctly classifies all of the visible data points. This means it has low bias. But as a result, it has also learned to separate out the outlier data points, which are actually confusing the model. This model will not generalize well and hence has high variance. We now have a good understanding of bias and variance up until now. But what's the trade-off? Let's cover that next. I will cover the mathematical proof later, but for now I want to introduce the concept at a very high level. So any error function can be divided into two parts, a reducible error and irreducible error. As the name suggests, one error can be reduced through different training algorithms and paradigms. The irreducible part comes through real-world data noise, which cannot be avoided, and the models have to be really careful about that. In real-world data, it's not very easy to differentiate between these two errors, because if it were, then machine learning would be a solved problem today. But that's also what makes this field interesting and fun. We are constantly pushing the boundary further away and getting as close to perfect models as possible. The reducible error comprises of two parts, bias squared and variance. This is where the trade-off starts to become more transparent. So now if we plot that previous equation, this is what it will look like. In the beginning, when we start training, the model is simple and has high bias. But as you continue training further, it'll reduce and reach its limit asymptotically. The variance, on the other hand, would start on the lower end, since the model is so simple that it probably predicts the same for all data points. But as the complexity increases, the variance should start to increase as well, and towards the end, it should reach overfitting levels. Now from this plot you can see that there's a sweet spot somewhere in between over there, where bias and variance collectively are low, and that's what we are aiming for whenever we train models. And this is exactly what that trade-off is. The trade-off is between model complexity, accuracy on training data, and accuracy on test data. As you experiment with model complexity, both bias and variance errors are moving in opposite directions, and you have to find that sweet spot to stop the training. In practice, cross-validation is something that's used to find this global minimum. To further understand cross-validation, you can watch my 60-second videos on it. I'll have the link to the video in the description. Now let's look into some ways of fixing this issue. Now if your model has high bias, then you can try training the model for longer, or you can use more complex models, maybe try out some nonlinear models. On the other hand, if the model has high variance, then you can use more training data, or you could stop the training earlier using one of those cross-validation techniques, or basically use a simpler model. Now actually let's move to my favorite part, which is actually the maths behind it. As mentioned earlier, I wanted to prove the error equation and show how the bias and variance terms show up in this equation. Let's get started. So let's pick mean squared error for this proof. Let y be the true value of the real world data and f hat be the predicted value. Now the error function would be expected value of y minus f hat squared. Now due to linearity of expectation, we can break this into individual expected terms like this. Again, continuing from the previous equation, let's pick expected value of y squared. So now y is a real world data value, so it would follow some f of x function plus there is some that irreducible error that I was talking about that gets introduced into real world data. Now if we open that up and following by linearity property, this is what the equation would look like. It's expected value of f squared plus 2 times expected value of f times the error function and plus expected value of error function squared. Now since f does not depend on the data, because that's going to be a constant value, we can leave the expected value out and it's just f squared. Now the noise that I was talking about, let's say that noise has a mean value of 0 and sigma square as variance. So now from the previous equation we can simplify those terms like this. And this is what our current mean squared equation looks like. It's f squared plus sigma square, which is the variance of the noise, minus twice of expected value of y times f hat plus expected value of f hat squared. Now let's pick the third term, which is expected value of y times f hat. Y, as we have previously mentioned, it's f plus the noise. And again, following the linearity property, this is what we can break it into. And since f hat and the noise are independent variables, we can break that multiplication into expected value of noise times expected value of f hat. And since the mean of noise is 0, the second term vanishes and we are just left with f times expected value of f hat. Now let's continue further with the equation. Now for the last term, let's go backwards. Let's write out the equation for variance of x. So variance of x would look something like this. Now if we were to simplify the term inside the expected value, we can break it out like this. And again, using the linear property of expectation, this is what we can break it into. Again, further simplifying some of those values, this is what we get. The second term, expected value of an expected value, you can just simplify it into a single expected value. And after simplifying, variance of x is equal to expected value of x squared minus expected value of x whole squared. We can write that as expected value of x squared is equal to variance of x plus expected value of x whole squared. Now if we look at that last term, which was expected value of f hat squared, we can write it as follows. Now let's write out the whole equation that we have until now. So mean squared error is f squared plus sigma squared minus 2 times f times expected value of f hat plus the variance term and plus the expected value of f hat squared. Now you see the first term and the third term and the very last term, if we combine that together, we can write it as f minus expected value of f hat whole squared. And then the variance term remains and the sigma squared term remains. The f minus expected value of f hat, that is actually the bias squared value. So now you can see we have proven that the mean squared error is equal to bias squared plus the variance and plus the irreducible noise that gets introduced into real world data. This is how we arrive at this equation. This is how we define that the trade-off exists between bias and variance. That's all that was on the agenda today. I know it's a lot to take in, but what I would suggest is that once you start working with real-world machine learning models, always think about what value is high, what can be improved further, and use some of those tips that I mentioned earlier in the video to reduce one of these terms and try to find that sweet spot. Again, thank you again for joining the channel. Hope to see you in the future.